Good day, ladies and gentlemen. You are welcome to our lecture number 7 on Mcen508, which is for electronics and drives. My name is Kibir Ahmad Sabubila, and today we will be looking at power conversion, that is, how to change electric power from one form to another, changing from AC to DC, or from DC to DC, or DC to AC, or AC to AC. These are the 4 basic conversions as we have seen in our lecture number 1, I believe. And there are different types of thyristor power converters, and they are given as follows. We have 6 of them. The first one is diode rectifiers. We call them uncontrolled rectifiers. The reason is simply because a diode has no control terminal. Just like a thyristor which has a gate that controls its operation, the diode does not have a control terminal. So that is why we call it uncontrolled rectifier. And we have what we call line commutated converters, or AC to DC converters. We call them controlled rectifiers because we use thyristors which have a terminal for the control. And number 3 is AC voltage or RMS voltage controllers, which are AC to AC converters. We also have another class of AC to AC converters. We call them cyclo converters. They are the AC to AC converters which are at low output frequency. And we have DC choppers, which changes DC from one level to another voltage level. And we have inverters, which changes DC to AC, the ones that we use in a solar power system, because we know the solar panels generate their power in DC, so we use inverters in order to change it to AC. So let us start looking at the first one, which is the line commutated converters, AC to DC converters. These are used for converting the fixed voltage, that is the input voltage which has a fixed value and has fixed frequency, which is AC in nature, that's our supply. We convert it in order to obtain a variable DC output voltage. That is, we change an AC signal into DC, and this AC has fixed voltage and it has fixed frequency, while the output that we get, it can be variable in nature in such a way that you can adjust the value of the output voltage. And they use what we call natural or AC line commutation, that is the thyristors. And these are controlled version because thyristor has a terminal for the control of the operation. Here is a typical single phase full wave uncontrolled rectifier circuit, that is the one that changes AC to DC, and we call it uncontrolled because we are using diodes. As I told you earlier on, the diode does not have control terminal, therefore we call this type of converters uncontrolled. And we are using a center tap transformer. As we all know, when the input is like this, you find that this diode D1 will be positive while this one will be negative, so that the D1 will be forward biased and this one will be reverse biased, so D1 will conduct this voltage. When the input signal changes to the negative polarity, the polarity here also changes. This will be negative and here will be positive, so that diode D2 will conduct, while D1 will be turned off because it is reverse bias, and the signal will be conducted still in the same direction. So in this way, we are changing the alternating current into DC. Though this one is not DC because it is also varying, but because it flows in only one direction, we call it a DC. And here is another circuit for a full wave rectifier, but this one is controlled because we are using thyristors in place of the diodes, but the operation remains the same. We have a center tap transformer, and as I've explained, in the post half cycle, a thyristor T1 will conduct, while the T2 will be reverse bias, and in the second half of the signal, the reverse is the case, just like in the previous case I have just explained. And we have different types of line commutated AC to DC converter circuits, which include the diode rectifiers. These are uncontrolled. I have explained why they are called so. And we have controlled ones, the ones that use silicon control rectifiers, that's thyristors. And they can be single-phase controlled rectifier, and they can be three-phase controlled rectifier. That is the SCR version. And this AC to DC converters, they have applications in different areas. The first one, they are used in speed control of DC motor in DC drives. They are used in UPS, that is uninterruptible power supplies, and they are used in high voltage DC transmission. They are used in battery chargers. At least these are the major areas of applications. So the next one is AC voltage regulators or RMS voltage controllers. They are the ones that changes AC from one voltage level to another. We call them AC to AC converters. And the AC voltage controllers, as I've said, they convert a constant frequency fixed voltage AC supply, that's our input. It is supposed to have constant frequency and fixed voltage. It will now change it into a variable AC voltage at the same frequency. The frequency of the input and the output is the same, but we have a variable voltage, that is the output voltage can be adjusted to have different values. And these AC regulators, that is AC to AC converters, they are used in different applications which include speed control of AC motors. They are also used in speed control of plants, domestic and industrial versions. They are also used in AC pumps. This is a typical block diagram. This is my input AC, and this is the circuit that does the control or the conversion, and this is the output terminal. A typical example is given here, where we have a single phase AC voltage controller circuit, that is AC to AC converter using a triac. A triac is also a family of thyristors because it has three terminals, one of which is the gate for the control of the operation. And as you can see from the diagram, this is my input, that's the source, and this is my output, which is the load. And the waveform here shows that the input is AC in nature and the output is also AC in nature. The only difference is the fact that while this one has fixed input voltage, the output can have different voltages, and this is what this line signifies. That is, you can adjust the amplitude of the output to your desired value. So we now move to cycloconverters, which are also AC to AC converters. But the difference between this one and the first one we have just finished is that this one, they have low output frequency. The cycloconverters, they are used for converting power from fixed voltage to fixed frequency AC. That is, my input should be of fixed voltage level and fixed frequency. Now change it into another AC with variable frequency and variable voltage at the output terminal. The cycloconverters, they generally produce output AC at lower output frequency. That is, the frequency of the output is lower compared to that of the input. that is, the output frequency is less than the input frequency. Their applications include in the traction vehicles, that is in electric vehicles where we use electric motors, and in the gearless rotary kilns. These kilns is nothing but a system that is used for supplying heat for baking. Basically, they use it for baking ceramics and bricks. This is the typical circuit diagram of the cycloconverter, where we have our input here, and this is the cycloconverter, and that's the output terminal. So the next one is choppers, and the choppers, as we have mentioned, they are DC to DC converters. Their function is to obtain power from a fixed voltage, that is, which is DC, and convert it into a variable DC voltage. The input is fixed magnitude, while the output can be of variable values. And we also call them DC choppers or DC to DC converters. And these choppers, they use the technique of force commutation to turn off the thyristors. The DC choppers are used in different areas, which includes the speed control of DC motors from DC supply. They are also used in DC drives for suburban traction, that is in electric vehicles, which are used in suburban regions, and they are used in switching power supplies. A typical circuit diagram for the chopper is given here, where we are using a transistor as the main converting device, and this is our load with freewheeling diodes. The function of this diode is to prevent back EMF in case there is inductive load. As you can see, the input waveform is DC in nature, the output is also DC, but the output voltage is equal to signal Vs, where Vs is the supply voltage. So the value you are choosing for this signal will determine what should be the output, and that is why we say it has a variable voltage output. Then we come to inverters, and these are the ones that changes DC signal into AC signal. They are used for converting DC from fixed voltage DC supply into AC output voltage with variable frequency, and fixed voltage or variable AC voltage depending on the design. Here is a typical block diagram. My DC supply here, and this is my inverter, which is force commutation, and this is the output terminal. A typical circuit diagram for inverter is given here. This is an inverter that uses MOSFETs, 4 of them in a bridge. This is my MOSFET 1, 2, 3, and 4, and this is my AC supply. And these 4 in a bridge form, they form a kind of oscillation circuit which changes that DC into AC. And of course, the output that is produced is mostly, it can be sinusoidal in waveform, but sometimes it is in square waveform, or we have other patterns. So ladies and gentlemen, this is the end of this class. This is lecture number 7. I urge you to watch over and over again. Thank you very much.